There we go. Okay, so we're going to be looking at Module 5, which is belt and chain drives. As I just mentioned, we're going to see some similarities here to the kinematics of belt and chain drives to what we had learned in gears, which was the previous module that we looked at. So I'm going to just kind of walk through our learning plan here so we can see what we have. You will notice here that, oh, I'm sorry, I have this here. I'm going to edit this right now. The, oh, it's out of there. I guess I'm going to get rid of this whole thing. I just don't want that video to be there. I don't think it really is. I don't know why it's kind of showing up. Okay, good. Um, Probably was from last term. So we're going to be looking at chapter 11 in our kinematics textbook. And like I said, this is going to cover both belt and chain drives. So we're going to be looking at applications, kind of getting them started, shy of, actually specifying part numbers out of catalogs. We're going to be using the book information, but we're going to be going through the process of having an application and making sure that we specify a full belt drive and a full chain drive for the application. Now, what am I doing here? Let's say, okay. As we look at, I'm going to go back out to the module. It's not letting me back up. So I'm going to go back out to the module. So that's our learning plan. We're going to have our PowerPoint there. So we'll walk through that in the next couple sessions that we have together. You'll notice that we have a sessions recording just like we have for other modules. I will put out there the lecture recordings that we're taking today. And then anything that's out there right now would have been from last year or previous terms that I would have taught this if you wanted to peek ahead for some reason. We do have practice problems associated with this learning plan, and they are going to be the example problems that we're going to be working in the chapter. And that's going to include example 1 and 2, which we'll be doing today. And then example 3 will be the next time that we're together. Reminder about the practice problems. The practice problems are a 0 or a 10. Remember, if there's 1 or 2 small things that you missed, you probably will get the 10 points, but I'll make notes on them. But if you are missing information, if you're not following the format that I'm going over in class, the whole intent of practice problems, and I know we're towards the end of the term, and hopefully we all understand this at this point, but I'm still getting things in that I'm not able to give 10 points for because there's a significant amount of information that is either missing or unreadable. If I can't read what you are writing, then I can't give you points for it. And I'm not going to spend time, trying to figure it out. All right. Remember, your second year students, we're getting ready to go out in an industry. Sometimes you're going to have to share your work with other people to be able to kind of make sense of things or to check your work. You have to make sure that it's readable and easy to follow. Those are the things that we're practicing here. So when I'm doing my practice problems or when we're doing these example problems in class, I'm giving you the formatting. And so if you're going off on your own, you risk not getting the points for this. And it's 20% of your grade. That's why it's I'm not going to say it's an easy thing to do, but by spending the time when we're in class here, paying attention, following along, or going back and reviewing the videos. I am recording this. That's why it's a 0 or a 10. I don't give 8 out of 10 or 7 out of 10 on the practice problems. It's kind of like, did you do it? Did you follow the format? So that it gives you then that basis for what's going to be expected in the homework. So anyway, so that's there. There are a couple questions here. Make sure you're answering the questions. So this week for this module, I'd like you to list 2 things that you learned in this module that were new to you, okay? And then I want you to name and describe one place where you see an application of belt drives in your everyday life or around. And then also an application where you see a chain drive, okay? So they're around us. I just want you to kind of, look around and see where those are. So that's going to be our practice problems. Then the assignment number 5 is going to be end of chapter problems that are assigned for you to do that are going to mimic or at least get you prepared from the practice problems. So using that formatting, using the equations, and probably a very similar problems that we would have done that you can then look at for process and such. So I think the first 5 problems are going to be belt drives. So after today's lecture, you'll be able to do, a significant amount, a little bit over half of the problems here. And then the last 3 are going to be pertaining to chain drives. So those we'll go through the next time we're together. I do have an answer key here with the final answers, but again, you're going to have to show all the work along that way. And then my expectation is that you're looking there because often you're not doing the problems when I'm around. So if you're unsure or just to gain some confidence knowing that you did the problem correctly because you obtained the correct answer. Okay. All right. So kind of our same format that we're used to, just a couple of reminders. So what I'm going to do is I'm going to go over to our learning plan. And I'm going to click on our PowerPoint presentation, which is going to correspond to the information found in chapter 11 of our textbook. Okay, so we'll get started here. So our objectives here are basically to look kind of in depth at belt and chain drive. So first of all, want to know, why and when would we use belt drive? So what are the advantages of it? Look at different types of belts that we may want to apply for industrial designs. Also analyze the kinematic relationships of 2 shafts coupled by a belt drive. This is where we're going to see some similarities to what we've already looked at in previous modules. Then we're going to transition over and we're going to then look at chain drives, and we're going to see a lot of similarities between chain drives and belt drives, but a little bit different, way of transmitting the motion and the torque, if you would. We're going to look at different types of chain drives, and then again, analyze the kinematic relationships and apply them to applications where we're going to be designing then a chain drive for an industrial application. So in the beginning here, they talk about belt and chain drives. Basically, they're used to transmit motion and transfer power between rotating shafts. This sounds familiar from what we did in gears, okay? But when we start looking at belts and chains, we're going to see some distinct advantages over gears because they offer the flexibility of center distance. When we had gears that were working in tandem with one another, the gears had to have a specified rigid center line where they would then have the ability to engage. So we don't have that ability to kind of move them apart or, closer together, where belts and chain drives offer us that flexibility. So if we look, for instance, on page 304, and we'll be revisiting this illustration as well, this is just an illustration of a belt drive, okay? We have the belts going around on the outside here, and these 2 are what we call shivs that the belt is going to actually be within. You'll notice here that as opposed to a gear drive, we don't have to have them right up against each other. They don't engage with one another. The belt actually offers the ability to change this center line, and that's why we call it a more flexible application, because space-wise, we can then span a distance, where with gears, it's not as easy, okay? We're more tied into what the size of the gears are, right? So that's one of the clear advantages that we end up seeing there. Gears become impractical, as it says here, when distances between shafts become large, okay? Because otherwise we're going to be putting idler gears, all along to try to obtain the same distance. So as we look at kind of a very standard application of a chain drive, for instance, you are not using bicycle for your application that you're going to specify for your practice problem. So don't use a bicycle, because I think that one's really easy, and we're going to talk about it in depth here, or not really in depth, but kind of in this application here. So find something other than a bicycle for your practice problems answer there. But the chain mechanism is going to transfer the motion and forces of the rotating pedal assembly to the rear wheels. So I think most of us have ridden a bike and have that experience. So hopefully this is something relatable. Now, there is velocity ratio that is going to appear here. So the velocity ratio of the chain can be readily altered by relocating the chain on different sprockets. So if you have, for instance, a 10-speed bike, a 12-speed bike, 18, 20, 24 speeds, whatever it might be, you have levers up on the handlebars most often that you have the ability then to change your gear ratios. And then you can feel the difference depending on the situation that you're in. And all that that lever does is kind of moves the chain to one sprocket or another, okay, so that you can obtain a different gear ratio. So changing velocity ratios on a gear drive is much more complex process. So if we wanted to change, for instance, in a gear drive, like we had talked about in our previous module, we would literally have to take out physical gears and then put back in different gears. All right. So it's not as easy as a process to change like we can for a chain drive. Now, flexible connectors, belt and chain drives are commonly referred to as flexible connectors. So belt and chains drive or belt and chain drive kinematics are exactly the same. That's why they're clustered together here. Okay. Now, so we're going to talk specifically about belts first, and then we're going to find, like I said, we're going to be able to kind of say, all right, then all of this applies to chains, but there's some distinct differences. So we're going to start with belts first. I'm going to zoom in here a little bit. So first and foremost, the function of a belt drive is going to be to transmit rotational motion. That's the kinematics part. And torque. That's going to be like the machine design elements part when we add force. We're not going to be worrying about forces or torques here in kinematics. We're just looking at the rotational motion, okay, at this point. And we're going to be transferring that from one shaft to another, okay? Belts provide a more smooth, quiet, and a relatively inexpensive way of achieving the very same thing as a gear drive does, okay? So it's low cost. They are readily available. If you go to any auto parts store, for instance, you're going to see probably, you know, up above hanging a whole bunch of belt drives, or belts. So they're an application in automobiles. They're an application in motorcycles. They're on snowmobiles. They're in a lot of different places. They're in appliances that we have, you know, around our home. So they're very readily available. And because of that, they're mass produced, which gives them the ability to have a lower cost. Okay. Most often in your designs, you are not going to make a belt for a belt drive. You're going to buy a belt for a belt drive. And that's why being able to, number one, size them appropriately, but then also be able to follow a process for specifying them is really important. The process we're going to use is going to be out of our textbook for our applications of belt drives for the problems that we're going to have assigned in the homework. When you are out in industry, though, what you are going to do is you're going to look at a vendor's catalog and follow their process, okay? And the reason I'm going to ask you guys, what do you think the reason is for that? Why wouldn't you want to pull out your kinematics book and walk through the process of specifying a belt drive for an application that you would have out in industry? And I'm going to pull the chat box out. Why would we want to use a vendor's application? Why would we want to follow their process and kind of, I'm not saying that the book here isn't valid, because it is, but why, if we have a specific vendor that we know that we're going to buy our belts from, so maybe Gates is a very popular belt manufacturer, why would we want to follow their process?
You're buying their belt.
Because you're buying their belt. I want more. So you know it can be manufactured and it's their standard. Okay, but why else? Why else? Think further down the line. Further down the line. Let's say the application is out in industry and all of a sudden a belt breaks and you're like, wait a second, that was supposed to last a lot longer. Replacements, yes. And so if it was supposed to last longer and you don't follow their process, what can't you do? If you're like, oh, I pulled it out of my kinematics book and I specified a belt that I thought was about close, but now it's not lasting as long as it should. Warranty. Yeah. You want to make sure that every possible warranty can be in place and that you can prove that you followed their process. Okay. That's why when I have you guys document how you write things out, You may need to do that when you're working for a company where you are specifying parts that you're going to be purchasing, whether that's belts, chains, bearings, anything that would be purchased that you're incorporating into your design. You can't just willy-nilly be like, that looks good enough. I think that'll be fine. You have to kind of prove that. And if there is a warranty issue, you're going to have to be able to say, yes, we followed your process and this is what I did. And this tells me that it's supposed to be there, so that now you have something where you can go back and, make sure that they honor that warranty. Also, let's say, even if it's something that breaks, what if somebody gets hurt out in the field? Okay, that's operating that machinery. And if you didn't use the process from the vendor to size that, your company or you could be liable for that. All right. So it is very important, especially when you have machinery where people are going to be interacting with it and you're going to be specifying and sizing elements. Okay. So make sure that when you are buying from a specific vendor, no matter what the purchase part is, okay, whether that is gears or belts or chains or, like I said, bearings, that indeed you're following whatever manufacturer's requirements are there, whatever sizing process that they have. All right, so we already mentioned they end up being low cost. The flexibility of that center distance, being able to get closer or further apart is huge compared to gears, okay? Belts are also going to operate more smoothly and quieter. When you're in an industrial situation and you go out on the shop floor, there's a lot of noises that are going around, okay? So if there's anything that we can do to bring that noise level down, that's always kind of nice, all right? So being quiet. In an automobile situation, we want to keep that noise down because that affects your experience when you're driving, right? You don't want to have this big loud piece of machinery that you're driving down the road. And that's part of what can make the operation more quiet. They also don't require lubrication like gears and chains do. Gears and chains are going to be metal on metal. So they're going to require, heat is going to build up. You've got metal on metal. Number one, they're, like we said, they're going to be a little bit louder, but they also require lubrication. If sometimes you don't have the ability to get lubrication efficiently to a drive, so belts kind of become like what you have to use. So always keep those in mind. They're easy to assemble and install. There's very little maintenance to them. You'll probably notice visually that you need to replace a belt when they start looking like they're fraying or cracking. Okay, you never want them to get past that point, so you want to do some checks on them. But for the most part, there's very little maintenance besides changing it out when it's time. And they also are better at absorbing shock loads because they have that ability to stretch. Okay. So the materials that they're made out of, most often they're going to be kind of a rubberized fabric, rubberized cord, reinforced plastic potentially, leather and fabric, and kind of a combination of different things. Many times we'll see them reinforced with either wire or steel in the middle of them so that it adds some strength. And there's a number of different types. Now the different types we're going to find on the top of page 303 in our book. So I'm going to go underneath our catalog here. So on page 303, here are some of the most popular types of V-belts that we see. So first, well, belt drives, I should really say. The first one is a flat belt. And this would just go over a flat type of a shiv. More popular are going to be what we call a V style. And this really speaks to the profile that we see here that looks more like a V. Okay. That V is going to fit down into the profile of a shiv. So if I look at, if you would, kind of a cross section of a shiv, the V belt is going to actually fit like snug down into that profile. So what that means is when you pick your belt, your shiv has to match because they're kind of a match set. You can't get, different sizes or shapes that are going to fit in that same profile of the shiv. Then you're going to have, multi-V belts. Multi-V belts offer the opportunity to have more surface area for which we are going to have friction that is going to transmit the rotational motion and the torque. So if we need more friction area or surface area than what one V-belt can provide, then we can actually get multiples, okay? Now, depending on the manufacturer, you can get multiples of usually 1, 2, 3, 4, but if you need anything beyond that, you're going to have to look at what they offer. There are some that are more than that, but they might not be 5, 6, and 7. You might have to, you know, find out what they have available. The next one that we have down here, you're going to notice it's called a cogged belt, and there's these little rounds here. That's when we have a bigger, chunkier belt that is going to be transmitting, you know, higher torques, if you would, and horsepowers through it. But because it's big and thick, we have to put the little radiuses in there so it can make a radius of a shiv. Okay, so it can like go or bend around a corner. That's what those are. They're not to engage with any teeth. Whereas when we have a timing belt, the teeth that we see on a timing belt indeed do fit into grooves on a specific type of sprocket, for which then they are going to act more like a gear or a chain drive. Okay, so let's see what we have here. I just want to make sure that we're kind of following along with our got that one done. Okay, with our PowerPoint. So now let's talk about shivs. The shiv is going to be the rotating, if you would, pulley, or shivs are what they're usually called when we're dealing with belts. They're going to be the wheels that are connected to the shafts and they carry the belt. So we've already pointed at what the cross section of a shiv would look like. Okay, the bore that goes through here, this is where it would actually mount to a shaft. A lot of times there's going to be a key that's going to be in there as well so that it rotates at the same RPM as our shaft. And then this would be what we call the hub. That's going to be the area for which the shaft is going to go through. Then on that is going to be the shiv, or like I said, sometimes they're referred to as pulleys, okay, in belt drives. And then you'll notice that there's a pitch diameter dimension here. That pitch diameter is going to be what we call the effective diameter, just like we see on gears. It's not the top of the tooth, it's not the bottom of the tooth, but what's going to happen is as this snugs down, I'm going to use this one as an example, as that snugs down into the V of the sprocket, what's going to happen is that effective diameter, or that pitch diameter, is going to be where the largest amount of strength or the highest amount of strength is built into the belt. So in this case, you're going to see that there are those dots. Those dots are typically going to be like wire that's running through that, made of metal, to add strength to the belt. That is where the pitch diameter. So when this goes down into our shiv, that belt might be physically a little bit above the top surface of the shiv, but where the pitch diameter is going to line up with that strongest area of the belt. Okay, and again, it's really just like the pitch diameter of a gear, where it's not the top, it's not the bottom, it's not even right in the middle. It's just it's that area where that effective diameter is going to be, and that corresponds to the pitch diameter on the shiv as well. Okay. They're going to be classified by their pitch, commercially available shivs. So when we look at table 11.1, you're going to notice that we have commercially available shivs. Now, this doesn't mean that these are the only ones available out in industry. Very often, companies who make V-belt drives or belt drives with shivs are going to be making all of the belts, the categories of belts here, and we'll talk about that in a bit, and the sizes that we see here. But a lot of times they're going to have their own additional variations on to expand their product line and differentiate from other competitors. So for instance, Gates does not just have a 3V, 5V, and an 8V belt. They have other variations on that for a multitude of different applications. But these are going to be kind of the standard 3 sizes that are going to be available. So their base product line, if you would match what we see here, but then they would have additionals beyond that, but that would come from their product category. Now, as we look down below, you're going to notice that there are those corresponding 3 different sizes, 3V, 5V, and 8V. And as you can see, as you look, the physical size of the cross section of the belt is what differentiates. So the 3 is going to be the smallest and the 8 is going to be the largest, okay? And then correspondingly, when we look here, all of the numbers that are inside, if you would, the column here are going to correspond to a standard sheave pitch diameter. So again, the pitch diameter is going to be the diameter that's going to be created by that effective diameter on the actual sheave, okay? So questions on that. When we're specifying our drives, when we get into a couple of these example problems, we're going to be looking to this chart to pick then a standard commercially available sheave from their list here in our book. But when we're dealing with a specific vendor, we would be looking at their specific catalog. Industrial selection chart. So if we turn the page and we look at figure 11.4, this is going to be a chart where we can actually select the appropriate size cross-section of our V-belt drive. So as you can see here, you're going to notice that on this chart, we see an area that is specific to 3V, 5V, and 8V. And at the bottom here, I want to talk about the design horsepower. Design horsepower, in the case for our kinematics classes, we're going to use whatever horsepower they give us in our problem. But design horsepower is going to also incorporate a factor that is going to adjust the horsepower to reflect the volatility of the application. So for instance, if I'm looking at an automobile application as opposed to a drive that is going to be for a rock crusher in a quarry, they're going to have 2 different levels of volatility, meaning overload on the quarry application, the rock crusher application is much higher than if we would be in an automobile situation, okay? So what that means is our design horsepower can change from what is given, for instance, off the motor or from our input, okay? But for our purposes here in kinematics, design horsepower and the horsepower coming off the motor will be the same thing. You will look more deeply at design horsepower when you do machine design elements next term. I believe you do that in spring 1, okay? Well, anyway, so as we look here, you're going to notice along the bottom, this is going to be your horsepower value coming off of your motor. So if an application says you have 20 horsepower, motor, that means that that's going to be delivered to the application through our belt. So we're going to find where number 20 is. We're going to follow that line then up to what corresponds to the RPMs or the speed of the faster sheave. Okay, so that means, for instance, if I have a 2,500 RPM application and we're pushing 20 horsepower, where those two come together, it's going to be in this area right here, which falls in telling me that you should consider a 3V belt. Okay, that's how you determine by horsepower and the faster rotating shaft on what the size you should start with your belt. Now, I always say start with, because then you kind of go through that design process, and if you need to, you can always adjust. And like I said, if you find that it's not big enough because we picked a 3V, then you can always go up to the next size, all right? If you find that your 3V works, then you're going to work with only the pitch diameters that are in the column for 3V. As well as if you find that 5V is your application or 8V, you're going to work within those particular columns to get the appropriate sizes that are available, okay? We cannot specify willy-nilly just a random diameter because, again, belt drives are something you're going to purchase and incorporate into your design. So you have to work with whatever is available. So right now we're going to use our textbook, like I said, but if you are out in industry and purchasing from a specific vendor, you're going to use their information in their process. Okay. The next thing that we want to consider in belt drive geometry is number 1, we want to think about center distance. We've seen that the center distance can get wider based on, the difference from a gear design, but your center distance is going to be the distance between the center of the driver and the driven shifts. Okay. Now, if I turn the page and we re-look back at figure 11.5 down at the bottom of page 304, we already kind of briefly looked at this application. My center distance is going to be the distance between my driver and my driven. Most often, just like in our gear design, the faster moving sheave is going to come off of wherever you're getting your input from. Most often it's going to be a motor or an engine or something like that. So your smaller sheave is going to be on the input. Whenever we see the number 1 in this chapter, that means that it's going to be the faster moving sheave or your driver, okay? Number 2 is going to be the slower moving sheave or your driven. So this is going to be, if you would, like the output. So input would be over here, output over here. And this was the same numbering system we used for gears. Ones were the higher moving or the pinion gear, and 2s were going to be the gear. Kind of the same thing here. This is the smaller moving sheave, and this one's going to be the larger. So with each one of those, you have a rotational speed associated with it. So you'll notice here that we have this lowercase omega, or like I refer to it a lot as W. So W1 is going to be the input on the driver side, and W2 is going to be the output on the driven side. Now, something unique or different from a gear drive to a belt drive is that you will notice the rotational speed direction for the input to the output remains the same. When we have an input to an output gear that are in engagement, pinion to gear, the rotation direction goes opposite all the time, right? We saw that in gears. But here, because they are not physically engaged with one another, like with the teeth of a gear, the rotational speed direction input to output will be in the same direction. So if your input is going in a clockwise direction, so will your output. Okay. If you need that to change, you can change it by just crossing the belt over. And you may have seen applications where this kind of happens, right? But that's what dictates it. So in kind of that standard mode, if you would, they would go in the same direction if you have the centers, in line with one another. Now, there is a center distance range that we want to live within, for instance. So you'll notice that it says D2, and then you have the center distance, capital C, in between. So your center distance needs to be greater than whatever the diameter is of your larger pinion, because remember, 2 is your output. Oh, and it has to be less than 3 times adding together the input and output pitch diameters of their sheaves. So we just need our center distance in there. It's a pretty wide range. So when you pick your center distance, you just want it to be within that range. And all that does is it just makes sure that if we look back here, that these don't get too close together, that you can't obtain the proper, we're going to find out, wrap angle. And you don't want them too far apart. There's a lot of sag between them either. So there's just kind of a pretty generous range that we have to be in, but we always want to check our center distance against that before we kind of, put the final blessing, if you would, on the application. Okay. Now, another thing we need to consider as we design and incorporate this into our design is that there's going to be stretch on the belt. Over time, as this runs under load, it just is natural that these are going to stretch out. So as part of the design process, it's not in kinematics here, but when you would incorporate into your job or into your design, you would then also account for what they call take up. Okay, so your belt is going to be nice and tight when it's first in its application, but like I said, over time, it's going to loosen up. We don't want it to jump off of the sheaves. So we have to put in, usually it's like a spring tensioner or something like that to take that up. And you may have seen that in applications that you've encountered. The belt length is going to be something that we also have to specify. Now, on V-belts, these are what we call continuous belts. Okay, meaning we can't, it's not like a chain where we can take the chain apart and we can wrap it around something and put it back together. There's not like a point that we can pull it apart. So this is what we call a continuous belt going over the whole thing. So we need to know how long that belt is as it goes over the circumference of each one of those sheaves. But in the geometry, we not only have to build in some stretch accounting for, like for instance, like a tensioner, like we had talked about, but we have to have the ability to physically move one or both of these sprockets in so that we can wrap the belt around and then tighten it up for its final application. Okay. Those are also going to be things that when you specify your drive from a specific vendor, they're going to give you the information about what you have to design into your process in order to properly get that installed. Okay. Let's talk about angle of contact. We'll look there as well. You'll notice that on our driver and our driven, they have this angle of wrap. That's the angle of contact or the angle of wrap for which the belt is actually on the sheave. Okay. That's an important number because we are going to be transmitting our motion and our torque using just the friction of the contact of the belt to the sheave. If we don't have enough wrap, we're not going to have enough ability to transmit that torque, and you're going to get your belt slipping all the time. Okay. So over on the right-hand side are the equations to make sure that you have the appropriate wrap. And that's where you see theta 1, okay, and theta 2. And you'll notice once we specify our diameters and we know what those are and we know what our center distance is, we can figure out those angles of wrap, and then we can compare them to what they should be. Okay. And we'll do that in an example. That velocity ratio. Let's look up at the top of page 305. Okay, 305. So over here, we've talked about velocity ratio when we looked at gears. In gears, we could do it with the rotational speed of the input to the output, which is our W's here. So notice that velocity ratio is equal to W1, which is going to be the angular velocity of our driver, divided by the angular velocity of our driven gear. So this would be our input, number 1, and number 2 would be our output, like to whatever we're driving. Or we can compare the radiuses or the diameters. So you kind of see those expanded out down here. So the only thing that we don't see in this list that we saw on gears was the number of teeth. We don't have teeth to count around the diameter. So we have to measure the diameter or know what the diameter is, or we have to know the difference in the rotational speed input to output. And then we can use those to calculate our velocity ratio. Okay. Now, just a reminder, I have this little note here. 1 is always the driver and 2 is always going to be the driven, okay, or the output. So input is going to be our 1, output is going to be our 2. I think this is on here as well. Belts, it says, transfer their maximum power at speeds of between 4,000 and 5,000 RPMs. It is best to operate belt drives within this range. That's a pretty fast speed, if you'll notice, okay? And the nature or the physics of a belt drive is that as it runs, it's actually going to snug down into that sheave, and it's going to give better ability, more friction to transmit the motion and the horsepower and torque that's required. Okay, so we'll be referencing back to this. Now, when we look at belt speed equation is going to be up here. It is going to be equation 11.8, which is at the top of page 306. Now, in your book, there is an error in the call out of the numbers here. Whenever we're finding the velocity of the belt. Now, the velocity of the belt, notice the variable here. It's a V. That means it's straight line velocity. If you remember when we did gears, we called that pitch line speed. It's the same thing, okay? But in this case, we call it the belt speed, all right? And that is going to be calculated using the radius of whichever sheave we're on. So if it's the sheave on our input or on our driver, we match it up with the rotational speed of our driver. The mistake that you're going to see here is this says R1 times W2. They have to match. That's an error. That's a typo. So your R1 has to be multiplied by your W1. You cannot take the radius of your input and multiply it by the rotational speed of your output. They have to be the same. So you'll notice then here over on the right-hand side, our R2 has to be multiplied by our W2. So make sure that those get updated there. Okay. Now, this is that equation that relates rotational speed, radius, and pitch line speed or straight line velocity to each other. So when we are trying to find pitch line speed or belt speed, in this case VB, VT and VB are the same thing. Okay, it's just that they're on different applications. You'll notice that our W has to be in radians per second. Okay, we cannot be in RPMs. So we'll always be given and we'll always report in RPMs. But when we're inside this equation, velocity, straight line velocity is equal to radius times angular velocity. Our angular velocity has to be converted to radians per second. Okay, just like we've been doing in other places, right? The last thing I want to cover before we look at our example is you're going to notice that table 11.2 on page 305. Here's another table of commercially available V-belts, but this is by the V-belt length itself. So the V-belt is going to come in a continuous belt. So for instance, it's going to simply be an oval shape like that, okay? And the length of the V-belt is if I would cut this, you know, at some point and I would lay it out flat, that would be the length of my belt. Does that make sense, everybody? Although we're not going to do that because it's continuous belt and we want it to go over our shivs, but it's really the circumference, if you would, going all the way around. That's going to be the length of the belt. The center distance is going to be between the two shivs. That's different than length. Okay, so center distance is going to be between the two shivs. Length is going to be if I would wrap a tape measure all the way around, how long would that be? So it would go from this point all the way around to that point. That would be the full length. Does that make sense to everybody? Okay. So that's what these numbers are in here. These are the standard commercially available V-belt lengths in inches for 3V, 5V, and 8V. Okay. So when we specify a full drive, we're going to be using the charts that are here. So we will be referencing this in our examples. All right. Okay, so let's look at our first example. And I just want to be sure, I believe that's our very next PowerPoint. Okay, now in example 1, we want to determine an appropriate industrial belt size, the operating speed and of the compressor and the belt speed for the application. So let's look underneath and look at the complete statement that we have here. So this is on page 306. It says we have a belt drive is used to transmit power from an electric motor to a compressor of a refrigerated truck. The compressor must operate when the truck is parked and the engine is not running. The 10 horsepower electric motor is rated at 3550 RPMs, okay? And the motor shiv has a diameter on it of 5 inches. Okay, so that's coming right off of the motor. There's a 5-inch diameter shiv on there. Now, the compressor, which would be the output machine. So the input is going to be on the motor side. The output is going to be the compressor, okay? That has a 7.5-inch diameter shiv on it. They want us to determine what is the appropriate industrial belt size based on the information we're given, the operating speed of the compressor, and the belt speed, okay? So what I want you to do, if we go back over here, using that statement, I want you to kind of look at these 3 questions. So what do you know? What's given? All right. And I want you to line up variables with what the problem statement gives us. And then I also want you to then be like, okay, given that, what equations am I going to maybe focus on to solve this problem? I'm not expecting you to solve the problem right now. All right. So those two questions right there, I just want you to be like, okay, the variables that I have to find are X, Y, and Z. And then the equations that I'm going to probably focus on are going to be this, that, and the other. So I want you to go in your book and kind of, page back and forth and kind of be like, all right, I want to determine the industrial belt size. I want to find the operating speed of the compressor. And I want to find what the belt speed is. So list what do you know? And then what equations do you think you're going to be using? You can peek ahead, and this is a shorter example. If you want to peek ahead, you can, but I challenge you to kind of look at this and try to find it, critically think about what's there. Okay. I'm going to give you a minute to kind of write this down in what would be the start of the problem. Okay. And then we'll look at it together. By the way, this is also your first practice problem that you'll be handing in. So you'll want to kind of start the problem on a, piece of paper so that you can then hand it in as well. And just take a stab at it. Even if you're not exactly sure, you know, what based on what you know about units, on what you know of some of the variables, some of them we've talked about in other places already. Just take a stab at what you think, the given information is. Like, do I know a W1? Do I know a W2? Do I know pitch diameters? Those types of things, and try to line them up based on what is given in this problem. Okay, as we look at the information that we're given here, okay? I have a couple things already circled, but if I look at the 3,500 RPMs, it says that we have a 10 horsepower electric motor rated at 3,500 RPMs. Now, one thing that you want to keep in mind, remember that our variables are tied to like a number 1 and a number 2. So I just put a little note up here. Remember that your number 1s are always your drivers. And in this case, that is going to be representing that electric motor. Okay. Your number 2s are going to be your driven. And in this case, they're referring to this compressor for the refrigerated truck. And so the compressor is going to be anything that's going to be a number 2. Okay. So our input is going to be that electric motor, and our output or our driven is going to be the compressor. So as we look here, 3,500 or 3,550 RPMs. Did anybody specify a variable for that one? What would that be? Yes, that would be the angular velocity W1 of our input is going to be 3,500 or 3,550, sorry, RPMs. And then we don't really have a variable for the horsepower, but we do know that the motor has a horsepower of 10. Okay, so might as well put that because that is going to come in handy when we want to specify that belt off of that chart. All right, any other variables? Do we know a W2? Well, do we know it though? I'm asking what we're given. We do not know a W2, okay? If you look here, it's saying the operating speed of the compressor. That is something that we need to find, okay? W2 is something we're going to have to find. So yes, we'll be able to get it, but right now, given, that's not given to us. What else are they giving us in this problem? What's something else that you wrote down for given? Emily's saying, yep, D1 and D2. So D1 is equal to D2 is equal to. So what is D1 equal to as we look up here? Remember, ones are our inputs off of our motor. Ben says the sheave diameter 5 inches. You're correct. So 5 inches is going to be D1. Yep. And then D2 is going to be the 7.5. Yes. Perfect. Okay. Anything else that you wrote down as given in this problem? No, those should be it. And then our find, we already know that we need to find the operating speed of the compressor. So that's going to be our W2. What else do we need to find? Anyone in the classroom? I'm not getting anybody in the classroom answering many questions. Classroom. What did you guys write down for find? What do you have to find here?
Also the belt speed of V.
The belt speed, so VB, okay. And, oh, Ben put in here belt size, right? Belt size. Okay. And I think those are the three things, right, in the last statement there. Appropriate belt size, the operating speed of the compressor, and the belt speed, okay? So they're not telling you, you got to find W2, you got to find VB, you've got to find, these things. You have to make sure that by the descriptions, you have to start kind of putting those things together. Okay. Now, what do we have available to us? So if we go back, we do have some equations along the way here. Now, I'm a big fan of let's organize this stuff, okay? So what we're going to do is we're going to take out an extra piece of paper and we are going to, starting on page 304, let's start writing out some of the things so that we're not having to page through here and try to figure out what's going on. So let's create an equation sheet for belt kinematics, okay? Belt kinematics. So I'm going to start an equation here. This is just going to be belt kinematics equations. Okay. And we're going to kind of, go through here. The first one that we have on page 304 is going to be this range for which our center distance has to fall. So this is going to be the range of center distance. Okay. And that's where our D2 has to be less than our center. So our center distance, that's this guy right here, has to be greater than the pitch diameter of our output sprocket. And it has to be less than 3 times the pitch diameter of our input plus the pitch diameter of our output. Okay. So this is the range for which our center distance for our belts has to be. Now, Center distance is going to be kind of a little bit of a strange thing for us because in the applications that we have, it may or may not give us a range where we have to have our center distance. So we might have to just pick one. Okay. In some applications, it may give it to us. You will know when you're out in industry, if you would, the application that you're physically trying to apply, you'll know the space that you have to work within. Okay. So you'll be able to give a better number for center distance. Now, the next one here, if we want to calculate our center distance. So if I wanted to calculate my center distance, this is kind of the middle equation right here. It's kind of a main one. But in order to calculate my center distance, I have to calculate this value of B. This is just a variable where I'm going to take 4 times the length minus 2 times pi times the pitch diameter of the input plus the pitch diameter of the output. Now, instead of putting this part where the B's are in this equation, to simplify it, you'll notice that the B's are kind of separated out. So you're going to calculate B first and then use it in the equation above. Now, because you need the length of the belt, okay, the length of the belt equation is above. So we need to really write kind of all 3 of these, all right? So length of the belt is here. So L, length of our belt, okay, that's going to be L is equal to, and this is the equation that you're going to write. So I'm going to put mine down here, 2C plus, now C is the center distance, plus pi over 2 times D2 plus D1 plus D2 minus D1, square that full quantity divided by 4C. Okay. And then my center distance, and this is going to be between D1 and D2. So if we look down over on the left-hand side here, our center distance is from the center distance or from the center of our input sprocket to our output. Okay, that's the center distance. That's going to be equal to the equation that we see here where B is going to be there. So write down those 2 equations so that you can reference them and just double check that you write them down accurately. And B really isn't a named variable. It's really just something that you calculate to make that equation a little bit shorter. That's all that it is. Okay. Then the next equations that I'm going to add are going to be, and I'm going to go up here to equation 11.7. This is going to be the velocity ratio between the driver and the driven sheave, okay, or pulley. So you want to write down these variations on the velocity ratio. So VR is equal to W1 over W2. That's the rotational speeds. The radius of the pitch diameters. And make sure you get the 1s and the 2s on the appropriate side or the pitch diameters themselves. Okay, so notice that 1 is on top for our rotational speed. 2s are on top when we're dealing with the physical diameters, the radiuses and the diameters. And then the last equation that you want to add, we're going to turn the page at the top of page 306, right up here. We want to use the equation for belt speed, and make sure that you have your ones together and your twos together. So we're going to call this belt speed, which is also pitch line velocity. VB is going to be equal to R1 times W1. Okay, but we also can calculate that by taking the diameter, pitch diameter of the pulley divided by 2 times its rotational speed. Okay, and then we can also say that that's equal to radius 2 times rotational speed of pulley number 2, or again, the pitch diameter 2 divided by 2 times W2. So make sure that you have your ones and your twos together. So I have my W1 and my R1 together, and my W2 and my R2. Now, a note that you want to put on here is that these W's need to be in radians per second or radians per minute. And I say radians per minute. If we're looking at belt speed, typically we are given, or they want us to report it, popular units for it are going to be like feet per minute. A lot of times is what you have belt speed reported in. Okay. All right. So using this, kind of organizing this, now what we want to do is going back to our problem 11.1. Okay. We need to find, for instance, I'm going to start with belt size. Okay. Belt size, really not an equation here. We're going to use the given information and we're going to pick it off of the chart. Okay. So we're going to go back to table 11. I'm sorry, figure 11.4. Okay. And this is where, this is going to be our industrial V-belt selection chart. And we're going to use the horsepower given in our problem. And we're going to find where it matches with the RPM of the faster shaft. Okay. So on our motor, we were given that we had 10 horsepower and that it was going at 3550 RPMs. Okay. That's going to be the input. That's going to be the faster shaft. So we are going to find where 10 horsepower is, which is right here. And we're going to line it up where 3,500 would be. Now, it's going to be a little bit taller than this line right here, but it lands within the application of what size? 3V. Exactly, 3V. Excellent. Thank you. So the first part of our problem is going to be our belt size. Going to be 3V, and you can just say from table 11, I'm sorry, figure 11.4. Okay. So if you would, that's kind of like the first part of what we have to find, okay? The belt size. Now, the next thing we need to do, we need to find one of these two, okay? What is the belt speed? Or what is the speed of the compressor shift, okay? So if we look back at our equations here, is there anywhere where we see the W's? Down here, right? Okay. Now, for instance, if we wanted to find W2, we know the diameters of both of the pulleys, right? We know the diameter coming off of the motor. We know the diameter coming that's going to be going to the compressor. So we know both of these diameters and we know the input RPM. So what we could do is we could use our velocity ratio relationship here where we know what the W's are, or we can take the W's and we can set them equal to the diameters. And we know W or diameter 2, diameter 1, and we know W1. All we have to do then is find the W2, right? Okay, so let's set that up as a ratio. So our second part here is going to be W1 over W2 is going to be equal to D2 over D1. Make sure you have them in the right order. Okay. Now we know, again, W1, D2, and D1. So what I want you to do right now, before we put the numbers in, let's rearrange this to solve for W2. Okay, so go ahead and rearrange this using your algebra to solve for W2. You get W2 is equal to D1 plus W1 divided by D2. Okay, go ahead and fill your values in then to solve for W2 from what you know above. Make sure you put your units in so that you can see the cancellation and that you end up with the appropriate units for W2. So for D1, we know that D1 is 5 inches. So make sure you put your units in here. Multiplied by W1. This equation, this is a ratio. You do not need to convert this to radians per second, okay? So we're just going to put in the 3550 RPMs for W1 right there. Then we're going to divide it by diameter 2, which is 7.5 inches. Now, cancel out any units top to bottom that you can get rid of. So it looks like we can get rid of our inches top to bottom and we're left with RPMs. Are those appropriate units for a rotational speed of an output? Yes. That's why you put these in there. Because if you didn't rearrange this correctly and you don't end up with the right units for the quantity that you're solving for, then you know you didn't set it up correctly. Okay. So I have to see those cancellations. I'm seeing those missing sometimes, and then I can't give you points. Or you're either getting deductions or you're getting, if it's on the practice problems, it's going to be 0. So W2 is going to be equal to, what do you get for a value for W2? 2,366 RPM. Of course, we want to be precise. Did anybody else? Yep. Okay. It looks like Emily got that same value. Excellent. And remember, RPM, because that's what we did not cancel out. So we would put a box around this as our final answer. Okay. So the elements that we've been practicing here are, we write our equation in variable form, rearrange as needed, and then we put our numbers in with units, cancel and or combine, and then you put your final answer. Do not leave this as just 2366.7 RPMs with a box around it. Why not? What was that?
What's that speed represent?
Exactly. What is it? I want it labeled. Remember, W2. If I'm solving for W2, I better see a box with it on the value itself. Okay. And I better be able to read it. Look back at what you're submitting. If it's grainy, if it's too close together, if it's too sloppy, I can't give you points. Okay. And you might be like, well, Kelly's picky. I'm gonna say one thing to you. Yeah, I am. But you're also not taking one test in this class. Are you? What would you rather do? Pay attention to details and make sure you hand it in the way I want it, because you're gonna have a boss someday that's gonna want things the way they want it. Or would you rather me give you 3 tests during the term? I think I know what I would rather have. I'm pretty sure I know what most of you would rather have. So yes, pay attention to these details. All right. That's why I expect them from you, because I'm not giving you tests, but I expect good, complete, readable work when you hand in for me. And you get more homework problems. You know, I probably wouldn't be assigning quite as much homework if I was giving you guys tests. For the simple reason is I'd rather you be doing problems than wasting a class time on getting a test taken, honestly. And I'm not sure if anybody, if you're working out in industry, does anybody say, clear your desk, I'm going to give you a quiz right now? Never. I never had that happen to me. Okay. So pay attention to these details. You might roll your eyes. You might think, oh, it takes me so long to do that. Yeah. Okay. It does. You get to do it once. All right. Somebody's going to be making this or going to be reproducing it or wants to look at it. You've got to be able to convey your information. Okay. All right. So that's W2. So now we need to find the belt speed. Belt speed. Looking at our equation sheet, looks like belt speed is down here, right? Okay. Now we know diameters. So you can just do the diameter divided by 2, or if you want to do the radius, that's fine. Now, we now know W2, and we do know the diameter of the compressor sheave. But would you agree that it's better to work with the W1s? Why? It is better to work with W1. Liam, I don't want you to say it. Oh, was it Noble? Okay. It's original information. We always want to try to give, or we want to use as much original information throughout the problem as we possibly can. Sometimes we have to calculate something, but then you've got to make absolutely sure that it's correct. If we made an error on W2 and we used it here, now all of a sudden our pitch line speed or our belt speed is not going to be correct. And I don't, Liam, I like you answering, but you seem to speak for the group in a lot of cases. And virtually, I like you guys answering too. Thank you. Do you guys ever have classes where you get a participation grade where you have to answer? Yeah, I've never done that before because that's another thing for me to keep track of, but be engaged. All right. That's the whole purpose of that. All right. So go ahead and write whichever version here using the W1s, whether it's the radius or the diameter, how you're going to solve. So I picked VB is going to be equal to D1 over 2 times W1. So again, I'm given the diameters up here. I'm going to use that up for the version of the equation. Now, as we look here, this is that equation where, as noted, we need to have our angular velocity or the rotational speed of our, in this case, our motor sheave in either radians per second or radians per minute. Now, as I said earlier, we're going to be reporting out belt speed. And if we look ahead to the final answer in our book, you're going to notice that they have that in feet per minute. Okay. So instead of getting this into radians per second, we're going to put it into radians per minute because otherwise we'd have to convert it back to minutes anyway. So over on the side here, we need to take our W1 from 3550 RPMs and get it into radians per minute, not radians per second, again, because we're going to be reporting in feet per minute. So go ahead and do that conversion. So radians per minute, there'll be one less conversion level that you have to do here if you would. You get 22,304 radians per minute. Perfect, thank you. Oh, or 305.3, okay, yep. Now what we can do is we're gonna use that value up here, all right? So we're gonna say D over 2. We know the diameter number 1 is 5 inches. So 5 inches divided by 2 times 22,305 radians per minute, okay? So I got 55,761.6-ish inches per minute. And we want to report this in feet per minute. So go ahead and do the conversion here to get this into feet per minute. Gonna have to. You get 46, 47 feet per minute. All right, I'm gonna put a box around this. Am I good to hand in? Noble says no. What am I missing? Exactly. Make sure they equal to VB, because that's one of your variables. And now we've got that solved, right? With the appropriate units. Notice I did my cancellations wherever I did unit conversions. Make sure you do that. Some people are writing this out without canceling. Well, how do you know what the proper units are? Okay. Make sure you take that extra step. All right, so if we go to the top here, I think we answered all three. Our belt size we got from figure 11.4. The rotational speed of the output or the second shiv going to the compressor, 2366.7 RPMs. And then our belt speed, 4,647 feet per minute. Okay, any questions? All right, these are fun. Okay, so what we're going to do is we have another example to go over, and that one's going to take us a little while. So given where we're at in our lecture today, I'm going to take a break. So it's 1:23 right now. So how about come back at about, what would 15 minutes be? 38? 1:38. What was that?
We can just round.
1:38. We're going to do 1:38. Otherwise, we sit here and we look at each other. All right, take a 15-minute break. Okay, so the second problem and the final problem that we're going to be doing today is going to be example 11.2 from our book. So, so if we go to page at the very bottom of page 603, I'm going to switch over here. This is going to be the problem statement for, and it's nice because this time they do have a an illustration for the illustration that we have here. So it says that we have a belt drive, which is right here going over the top of the two shifts, to reduce the speed of the electric motor for a grinding wheel, which is over on this side as shown. Okay. We have a 50 horsepower electric motor rated at 1725 RPMs, and the grinding wheel has a speed of approximately 600 RPMs that's going to be desired. So determine the appropriate belt size and find the suitable shiv diameters of stock pulleys listed in table 11.1. Also select an appropriate belt length from table 11.2 and calculate the corresponding center distance. Okay, so in this problem, you're going to notice that we are not given the physical distance that these need to be apart, all right? And that's where, when we get to the center distance part, we'll kind of work through that. But most often, especially out in industry, you are going to be able to kind of walk up to this and kind of know, like, what should my center distance be about? What am I trying to achieve here? So sometimes in the problems that we're given here in class, they're a little bit vague. Okay. And in some cases that's helpful. In other cases, it's like, well, what do I pick? So we'll kind of cross that when we get there. So what I want you to do to start off here is, first of all, I'm going to go back to our PowerPoint presentation. I want you to do that very same thing where list the stuff that you're given and line them up with variables from that equation sheet that we just identified. Okay. So anything that is given, and then also let's identify anything that we need to find. Okay. That way we kind of organize the information that we have. Okay. So go ahead and take a minute to look at that problem statement, see if you have any W's or D's or, anything that you can go on for this particular problem. This is going to be another example that you will be handing in for your practice problems. So from the problem statement itself, here are the elements that hopefully you picked out. If not, make sure that it kind of makes sense what we have here. So our W1, which is going to be our input off of the motor, is going to be 1725 RPMs. Okay. And that's a motor. It has 50 horsepower. All right. So if you would, that's the motor. W2, which is the grinder, they say they want it to operate at about 600 RPMs. Okay. Now, this wasn't in the original problem statement, but it's important to note because it's actually a little bit further if you look at the illustration here on page 607, there is a statement here that they want the belt speed to be between 4,000 and 5,000 feet per minute. So you want to make sure that your VB is between these two numbers here. Okay, it's a little bit further into the problem, but it's worth noting because when we look at what we have to find, that's going to come in handy. So we need to determine belt size. Okay. We need to find the sheave diameter. So we need a D1 and we need a D2, one to come off the motor and one to go to the grinder. So when we look at our illustration here, this one would be D1 and the larger one is going to be D2. Okay. Then they're also wanting us to select a belt length. So we need to know what L is, capital L, which is going to be the overall belt length. And then the corresponding center distance. Okay. This is a very practical type of an application that you would see out in industry. Okay, truly. Because all they're giving you is, okay, the motor that you have to deal with, and then what you want your output speed to be. And then also how fast you want that belt to be going, an optimal speed. Okay. And then from there, you get to pick the diameters, you get to pick the belt size, you get to pick what your length of your belt is and what your center distance is going to be. Okay, very practical problem. All right, so where do we start? We'll kind of follow along with the process that they took in the book here. So first of all, they went ahead, step number one was determine the appropriate size belt. And that is where everything starts because we can't pick commercially available size pulleys until we know what belt size we have, right? And that's the 3V, 5V, or the 8V. So we're going to go back to page 304 at the top here. And we want to give in the information of 50 horsepower and the speed coming out of the motor at 1725 RPMs, find the appropriate size belt. So look on your chart. Everybody should be looking in their book and finding which belt size is appropriate here. So you're going to find your horsepower on the bottom here. That's 50, right? So it's going to be along this line right here. And we're going to find where it meets with 1750. So 1750 goes over, okay? 50 comes up here. All right. So what would we pick for? Tyler says 5V. Anybody else agree with 5V? Yeah, I think that's appropriate, right? 3V, it's close to the line, but it's not over there. And actually, I'm going to tell you, this kind of is like if you would for this range, it's in the beginning of the 5Vs. All right, that's good. That means that we're actually towards the bottom or the beginning of where we would actually start sizing for 5V. If this was, let's say it lined up right there where it's still in 3V, but it's close to the 5V, I would cross over into the 5V because if you would be on this side of that line where the 3V is, that's like at the end of the applications for the V3. Does that make sense? You always want to either be at the beginning of an application of something or in the middle. You try not to be towards the end. Does that make sense for everybody? That's being a little bit more conservative designer. All right. You don't want to push that envelope because that means that you could maybe have premature failures or excessive vibrating or things like that. Okay. So always be on the more conservative side is the better side to be on. But we are at the, if you would, beginning of the 5V. So 5V is going to be our belt size. So step number one is going to be 5V equals the belt size. And that's from figure 11.4. Okay, so this is one of the things that we were looking for, 5V, so that would be done, right? Now, we need to know that because now we can start picking what our appropriate diameters would be, okay, for our sizes. So if we look where 5V is, and we go back to table 11.1, 5V has all of these commercially available diameters for us. Now, what we do need to do is we need to determine where we need to start there. So if you recall, oops, on our equation sheet here, we do have a condition of our belt speed needing to be between 4,000 and 5,000 feet per minute, right? And we know our rotational speed of our motor or our input, right? So if we know a range, 4,000 to 5,000 for our straight line velocity or our belt speed, we know what the rotational speed is. We would have to convert it to radians, per second or radians per minute. We can then calculate the radius or, if you would, the diameter, right? Okay. So we're going to use this equation right here equal to VB, and we're going to solve for D1. Okay. And we're going to find out, and we're going to pick something that's close. So let me go back to over here. My step number 2 is going to be, I'm going to take that pitch line speed. It's going to be equal to D1 over 2, because that's the radius of the pitch diameter of the sheave that's going to be on the input, multiplied by W1. Okay. Now, We know VB is supposed to be between 4,000 and 5,000 feet per minute. So that's, we know this value, all right? We know W1, but remember, this has to be in radians per, and we'll talk, it'll be radians per minute because we want this to be in feet per minute, right? So our only unknown here is D1. Go ahead and rearrange this equation to solve for D1, okay? Do the algebra real quick, and then we'll compare in just a second. So solve for D1, the unknown variable in this equation. You should come up with 2 times VB divided by W1. Did you get that same thing algebra-wise? Okay. So now that we have this solved for, go ahead and plug in your values. Okay, so this is going to be 2 times. On top is going to be our straight line velocity. Now, our straight line velocity is given to us as a range, 4,000 to 5,000 feet per minute. Okay. In the book, I believe they did 4,500. Yes, they're using 4,500 feet per minute. So we want to put in, we'll use their numbers to start out with, 4,500 feet per minute. Do not use the slash. They do. Okay, don't use the slash. We want to go to up, top, bottom for our units, feet per minute. Divided by, now we have our W1. Remember, in this equation, we need to be in radians per minute, okay? Because we have feet per minute on top. We want to be in radians per minute on the bottom. So what do we need to do? Can we go ahead and put in 1725? No, that's revolutions per minute. So we need to get this into radians per minute. Go ahead and convert W1 into radians per minute. So you should have 4,500 feet per minute on top divided by 10,838.2 radians per minute. Do you have that? Same number?
Yeah, I'm fine.
That's fine. Depends on what you use for pi. Okay. Remember, when we're talking about tens of thousands of things, 0.3 of a radian per minute is not going to make a big difference.
Different, but if I take it.
Okay. So it looks like, yep, Emily's got that as well. Good. So now you want to cancel out the units. The per minute, top to bottom, is going to cancel, right? The per minute's going to cancel. If we look at our quantity that we're solving for, what are we expecting units of? Distance, right? So what's left here? Feet per radian, right? Is that appropriate for a distance? Think. What happens to a radian when it's combined with something else? What happens to it? It magically what? It goes poof. Yeah. It disappears. So feet are your units that are left here. That's a distance. So that's good. So we're going to get our D1 is going to be equal to find your value, 4,500 divided by the 10,838.2. I'm getting 0.4152 feet. Is that what you guys got? Or something very close? Oh, why do I, why did you get 0.8? Kelly is wrong. What did I forget to do? I forgot to multiply by 2. Absolutely. Yes. See, I was testing you. No, it's easy to forget. I was not testing you. So I got 0.8304. Okay. Now, if we look at our chart, we look at our chart to pick our diameter because we're going to be picking the closest diameter on table 11.1. So we're going to be in this middle column here. Okay. Do you see that this is in units of inches? So what do we need to do with the number that we just calculated? Convert it, right? We know that in 1 foot, there are 12 inches. So our D1, what is that value in inches? I got 9.96 inches. Do you guys get that? So almost 10 inches. So now what we want to do is we want to take this number and we want to see what is on our chart, okay? What is on our chart? So when we look here, we want to look for something close to 9.96, okay? There's 9.7 and then there's 10.2. Which one do we pick? You're the designer. Either one of those would be fine. We don't have an exact number, but we want to pick one of those two. Let's see what the book picked. I don't know. They picked 9.96. Okay. They got 9.96. So 9.7 is what they picked for their value. Okay. That's what they picked for their value. So we're going to go ahead and we're going to say, all right, D1 is going to be equal to 9.7 inches in diameter, and that's from table 11.1. Okay, so that's what we're going to be going with. That's our D1 for right now, because that's a commercially available shiv. Does that make sense to everybody? Okay. Okay. So now let's look at the next step that they took. Okay. The next step that they took is they went ahead and they wanted to determine, I'm sorry. Oh. Oh, we have to determine, this is where we're at. I'm trying to figure out because they did it a little bit differently than we did. We want to determine what is our D2 now, okay? Our D2 that we want to get. So we know that our rotational speed needs to be approximately 600 RPMs, right? 600 RPMs. So we also know that our input is 1725, and that's where our D1 that we've chosen now off of the chart, we know exactly what it is. So we can set this up as a ratio like we did on the last one. So our step number 3 here can be using that velocity ratio where we can say W1 over W2 is going to be equal to D2 over D1. Now we know what D1 is, right? We know that D2 or W2 is supposed to be approximately 600 RPMs, right? So we'll use that as its value. And we know that W1 is 1725 RPMs. So we just need to solve for our D2 here. Okay. So that means that D2 is going to be equal to W1 times D1 divided by W2, right? Just rearranging to solve for D2. Right. So now we're going to put our values in here. 1725 RPMs times 9.7 inches divided by 600 RPMs. RPMs cancel, and we're left with inches. Is that a good number for a diameter 2? It is. Yeah. So go ahead and find out what you think your number should be to obtain this ratio. Okay. Did you get a value of about 27.9 inches? Okay. So now remember, we have to pick things that are close to, or we have to pick a commercially available shift. So we're going to go back to table 11.1, and we're going to look, is there a 27.9? There is. It's right at the end here, right? So it is commercially available. All right, commercially available. So 27.9, actually exactly, it came out right, would be our commercially available D2. Now, if it is something that is different or has a, is going to be, either larger or smaller, then what we may have to do is pick a different shiv for the D1 and then go through that same process again. Does that make sense to everybody? Okay. All right, 27.9. So that means that if we go back up here, we have our belt size, we have our D1, we have our D2 identified. Now we need to do our length and our center distance, right? Our length and our center distance. So if we go back to our equation sheet, we have our length here. It needs a center distance. And then you're going to notice that it's kind of like a chicken and an egg situation. For my center distance, I need the length. Okay. So what we're going to do is we're going to pick a number here that has to be between this range. Okay. Because we've got to pick one of them before we can pick the length. Now let's just see what the book picked. All right. Just so that we can kind of go along with what they did. So down here at the very bottom in step number 5, okay, you'll notice that we have to have our center distance between that range. So we'll write that very same thing out, making sure we understand what they did. So this is our step number 4. They did a step number 5. So we know that our D2 has to be less than the center distance, but then the center distance has to be less than 3 times D1 plus D2. Okay. So basically we have this. And now we just want to put our values in. So we know here our D2 that we just specified was the 27.9. So that means that our center distance needs to be greater than 27.9. And then our center distance is going to be, and then it has to be less than adding the 2 diameters together and multiplying by 3. So 27.9. Okay. And our D1 was 9.7. We're going to add those 2 together, and then we're going to multiply by 3. Do you get 112.8-ish? Okay. So all that this is saying is that it would be appropriate to have your center distance anywhere between those 2 numbers. This is just identifying the range. Okay. Now, again, this is a wide range. There's a lot of difference between 27.9 and 112.8, okay? But we just don't want to go outside of that range. And you would be able to probably walk up to your grinder if you were working for a company that made this arrangement, this machine, and you'd be able to be like, about here, okay, and you would pick a center distance. Let's see what the book decided on. So if we go to, did they do it over here? Oh yeah, they did. At the very bottom, the very last sentence here, they said, how about we just use about a mid value, which would be about 72 inches. So that's the only reason that they picked 72 is they just picked it out of the air, if you would, that satisfied this range. Okay. So we're going to use a center distance then of 72. Okay. So our C is going to be 72 inches. All right. That's where we're going to start. Now, we're going to use that center distance to calculate the length. Okay. So our L is going to be this equation right here. We've already got our D1s and our D2s, and we've already determined we've now got like a center distance that we want to pick, okay? We want it right around 72. So go ahead and write this equation out and put in your known variables, okay? So this is going to be 2C. Make sure you write it in variable form first. Pi divided by 2, D2 plus D1 plus D2 minus D1. Don't forget to square that quantity on top. So this is going to be 2 times 72 inches plus pi over 2 times 27.9 inches plus, let's forget what that was, 9.7 plus make sure you put your units in every form so that you can verify that you're going to end up with inches plus inches plus inches. So you're going to square the top here. That's going to be inches squared divided by inches. So you'll end up with inches for the last quantity. Okay. So go ahead and once you have your values in, calculate your number here for the length based on that exact center distance. I got 209.4 to start out with, but I didn't verify it yet. So let me know if you get that same number. Excuse me. Oh, we used 10.2. They use 10.2 for their diameter one, so their number is going to be a little bit different than ours. We use the 9.7. So did anybody else get 209.4 for your length? Miles did, looks like Aaron did.
I got 204.
What did you use for your D1?
97?
9.7, okay. And you use the 27.9? Double check, because I'm pretty sure 209 is correct.
10.2.
210.2, yeah, a little bit of rounding, probably because of the pi. Okay. Make sure you square this value over here before you divide by 4 and 72. Okay, try it again. Anybody else get the 209? It looks like we've got it confirmed a couple times in here with one difference. Two oh 4.2. Is that what you got too, Aaron?
Yeah.
Okay, I'm gonna try mine again. Oh, I got the 204.1 or 204.2. So maybe, see? I'm wrong. So since we've got a couple people, so double check if you got the 209 or the 2010, make sure you've got the same numbers that we have here. Because yeah, I think the 204 now is 3 people. Miles, did you get the 204?
Yeah.
You did? Okay. And Liam, I know you were 210. Okay. And 204.9 is what they get, but they use the 10.2 in their problem, so a little bit closer. All right.
Oh, I got 204.
You got the 204 too? Yeah. I don't know why. Felt like I was solid in the beginning. Okay. So 204.2 is what we're going with. So let's now take this length. Remember, this is a continuous belt. So we have to pick a belt that is like on the chart. So let's go to page 304 or 305. And this is going to be table 11.2. And we're going to go into the 5V belt lengths. Okay. 5V belt lengths. And we want to find something close to 204.2. And you'll notice here that there is a 200. Okay. There's also 190 and there's 212. The closest number is 200. Would you agree? Yeah. So that means that we would then specify our length, okay, our actual length. We'll say actual L is going to be 200 inches. And this is from table 11.2. Okay. Now, remember how we picked a center distance randomly, 72 within that range. And now we calculated a length of a belt that we needed was 204, but now we've changed this. So do you see how we have to recalculate our center distance to see what it actually is? Because now we've got an actual belt. Does that make sense? So we had to calculate, if you would, a length to kind of find out where we're at. And then we had to pick one from our chart. But now that we've picked one to be exactly 200 inches, we're going to recalculate to get our actual center. Okay. So we're going to go back to over here and we're going to calculate our center distance. But remember these B's in here, they are using this equation right here. So you have to calculate B first and get a number for that based on the 200-inch length that we just chose. Okay. And then we're going to use that B up in the equation here. So I'm going to calculate our B first. B is equal to 4 times L minus 2 times pi times D2 plus D1. Okay. So let's get our B. It's going to be 4 times 200 inches minus 2 times pi times 27.9 inches plus 9.7 inches. Okay. So our B value You get 563.8. That would be inches. Miles got that. Tyler got that. Okay, good. Okay, so this B value then, we are going to use in the actual center distance equation right here. Okay. So now we're going to calculate the actual, I'm going to put ACT underneath here. It's going to be equal to, this is going to be our B value plus the square root of, and you can kind of see why they did it in two stages here, because otherwise this would be kind of a crazy equation. B squared minus 32 times D2 plus D1 squared underneath the radical there, divided by 16. Okay. So C actual with the numbers is going to be 563.8 inches plus under the radical, that same number, 563.8 inches squared minus 32 times 27.9 inches plus 9.7 inches squared. And then all of that divided by 16. I'll do it again, but I'm pretty confident in my number here, 67.87. I got that twice. So I did get that number twice, so I'm very confident in the 67.87. And I think theirs came out to be, it says 71.98, but they did use the 10 point. They did use the 10.2 inch here instead of the 9.7. All right. So as we look back at our problem, what's the beginning here? Hold on. Did I turn it up? Yeah, good. We just calculated our overall length and our center distance. So we have all of the items here. So make sure you have boxes around with the variables identified and units for the final answer for the center, the final for the length, okay, from the table, and then also for the diameters you chose, the commercial diameters, as well as the size of the belt, okay? So this is a pretty comprehensive problem, which will mimic, I think, one of the problems that you guys end up doing. So use this as your guide, okay? So any questions on 11.2? Or do you need to see any part of it to be sure you have what you need? Okay. So that's as far as we're going today, as far as in the chapter. I think that's enough. All right, that's plenty. But let's look at which part of our assignment number 5 you could actually do for the belt drive stuff. So what that means is we're going to go to Canvas, and the next section you're going to notice here is going to look at chains, and we will look at chains the next time we're together, which is Wednesday. We're going to look at assignment number 5. Okay. and we're going to take a peek here at what homework problems would apply to what we've already done. I believe through 18, we should be good, but let's take a peek. So these are all at the end of the chapter. Okay. So the first one here is going to be 11.2. It says a motor operating clockwise at 1150 RPM is coupled through a belt drive to rotate an industrial exhaust fan. The diameter of the motor sheave is 5 inches and the sheave on the fan is 12 inches. Determine the speed of the driven sheave and the belt speed. Okay. So you have what you need for that. That would have been, I'm going to say that first example that we looked at was very close to that. The next problem you have is we have an engine coupled through a belt drive to rotate a generator, which must rotate at 11 or 1800 RPMs counterclockwise. The diameter of the engine sheave is 6 inches and the sheave on the generator is 9 inches. Determine the required speed of the engine and the belt speed. Okay, so the engine is the input. This is actually W1 and the generator is the output. Okay, so it's a little bit different. It's actually just rearranging. Okay, so that's number 11.6. You would be good with that. 11.8, we've got two sheaves have a diameter of 5 inches and 12 inches. Determine the center distance of the drive utilizing a 72-inch belt and compare that center distance to the ideal range. Also determine the angle of contact over the smaller sheave. We didn't do angle of contact in the two examples that we did, but there are two equations here, and I'm confident that you can determine what theta 1 and theta 2 are with these two equations right here using the center distances and the diameters, okay? So I'm really confident that you can do that. So yes, we didn't do an exact example with that one, but you have what you need in order to get that done. So that one's number 8, okay? Number 12 is going to be a belt drive desired to couple a motor with a mixer that processes corn syrup. The 25 horsepower electric motor is rated at 950 RPM. And the mixer must operate at 250 RPM. So the mixer is the output and the electric motor is going to be your input. Select an appropriate belt size, the commercially available sheaves, and a belt for this application. So that means you have to know what the overall length is so that you can purchase that belt. Also calculate the actual belt speed and the center distance. Okay. That's very similar to the last problem we just did. Okay. And then the last one that you have, oh no, this is chain kinematics, not 18. So through 16 is through 12 is the problem that you can do. Did we have a 16? Why do I feel like 16? Nope. So the first, it looks like 4 problems are going to be the ones that you can work on based on belt kinematics. And then the last 4 are going to be chain. Okay. So the next time we'll finish up with the chain stuff and then you'll be able to finish up this assignment. Okay. So, so that's as far as we're going to go today. I'm going to go up here. We're going to stop the recording.